Hey everyone, I am super honored to be opening Global Scope. It's a great lineup, lots of great presentations and folks kind of coming after. And Web Directions always does such an amazing job with their events. And I love events like this, like the single track focused on a narrow subset of the web, so you can go nice and deep on the topic. Although I guess you could argue that today's focus, JavaScript, isn't particularly narrow, at least not anymore. If you look back at kind of where JavaScript came from, I always felt like it had the most humble beginning out of the three sort of core web technologies that we see on the front end: HTML, CSS, and JavaScript. HTML, the OG, kind of kicked everything off, right? Like you can't do anything without the markup. CSS started with specification. JavaScript, though, was sort of the love child of two separate approaches to add scripting capabilities to the web. Two different browsers, two different approaches to scripting, took two different names. There was no standardization or specification at all up front. So the JavaScript stuff kind of came along a bit more ad hoc than the other two. And you fast forward today and it is all over the place. JavaScript no longer just runs in the browser on the person's device. We now use JavaScript to increasingly power the backend, running it on the server with Node. Thanks to, edge computing, things like Cloudflare workers or, Fastly's edge compute or Akamai's edge workers, we now can run JavaScript on the CDN layer, letting us do incredible customizations and personalization off of the client browser and on that CDN layer instead. JavaScript, for a while now, has been powering the most popular build tools, extending what developers can do. We've seen it infiltrate all of these key parts of the stack. Developers love JavaScript. Looking back at the 2020 version of the Web Almanac, this is a report that's put out every year, powered by HTTP archive data, which catalogs millions of sites so we can see the characteristics of how those sites are built. One of the things that the markup chapter revealed is that the sixth most common HTML element, the sixth most widely used element, was the script element. Well, first off, sixth place, depending on, I guess, what of an overachiever you were as a kid, sixth place may or may not sound all that impressive, but do consider that there are somewhere around 130 elements in the latest version of the HTML spec. So sixth place is pretty darn good. Also, if you look back historically, they compared in that chapter to 2005, where there was an attempt to try and catalog again the most common elements. Script wasn't even on the list to be found. Now it's sitting there right outside the top 5. We use the script element more than we use the paragraph element, which, is a little bit alarming to me, right? Like it's a little unexpected. That order I would have expected to at least those two elements be flip-flopped. But we love our scripts, and we send more weight down than ever before. If you look at the median bytes by content type that we send to a mobile device, we send 427 kilobytes of JavaScript. Now compare that to markup. We send 27 kilobytes of HTML or 66 kilobytes of CSS. That is a dramatic difference. Now the upshot of all of this JavaScript is, again, we've extended what the front-end developer can do. We can touch all sorts of different areas of the stack, and we can also create some incredibly immersive and rich experiences. Now, this example from Sarah Drasner is a few years old at this point, and yet every single time I see this, I am just blown away. The transitions are so seamless and fluid and frictionless. You see things kind of morphing and transitioning from one state to another, which can be a really great clue to the user, like how things are changing and how data and different views are connected to each other. It's just a really impressive view, and certainly something that 10 years ago I would have never thought possible, right? And this is the kind of thing we can do now because of how powerful JavaScript has gotten. But everything has a cost. And one of my favorite things to say, I've been saying it for years, is that everything you add to the page better have value, because everything absolutely has a cost. And that's true for JavaScript, perhaps especially true for JavaScript. WebAIM, Web Accessibility in Mind, does an annual report where they look at how many accessibility errors can they identify on any given page. One of the things they break that down by is when they can detect a framework or library is being used. So what you see here are two different tables showing frameworks and libraries detected on home pages that they've tested, and the average number of accessibility errors. That last column, that percentage difference, is the difference between, for example, pages with React running and the average page period. So what we see here is that every framework and library, with the exception of React, which is notable, I think, because React, tends to get beat on quite a bit when we talk about these things. But every other framework and library is widely associated with more accessibility errors than the average page online otherwise. We see the same thing from a performance perspective. JavaScript is very tightly coupled to how well a site or page performs, and it's easy to shoot ourselves in the foot. Jeremy Wagner, who's got a great book coming out called Responsible JavaScript. If you enjoy any part of this conference, I highly recommend checking that out as soon as it's available. But he looked at HTTP archive data, and what he did was he broke down the main thread processing time by category. So looking at HTML parsing time versus script processing versus style layout versus rendering and painting. Now, what he was after here was, how does that differ when we look at those percentiles, both the starting point and sort of that long tail? And what you see here is that at the beginning, JavaScript processing is pretty much in line with the others. But very quickly, as soon as the 20th percentile, 15th percentile, actually, we're starting to see a little bit of a separation there. Script processing takes off. And once you get to that P75, it is an exponential difference between that and the amount of time we spend on these other tasks. Now, the so what here, the thing that I find fascinating, is that this means that it is way easier to shoot ourselves in the foot with JavaScript than it is with these other tasks. It is comparatively difficult to cause all sorts of havoc on the main thread from anything else, from HTML parsing, certainly, but from scripting or styling, from rendering and painting. Script blows that away. It's an easy thing to destroy the performance of our site if we're not careful. So what I want to do now with the rest of this presentation is let's dig in. Let's look a little bit at how we're using JavaScript, what we're using, and what the implications are there. And then let's see if there are a couple things that we can do to hopefully offset some of the costs that we're paying up front. So again, going back, let's start with the size here. The median mobile site is sending 427 kilobytes of compressed JavaScript down. Now, this is problematic for a few reasons. The first, and probably the most basic, is just the impact that JavaScript has on the initial loading state of our pages and applications. When a browser is parsing the HTML and it finds a script element, it stops everything. It stops parsing the HTML. It doesn't try to request other assets. It stops until that script has been downloaded and then executed. Now, once that script has been downloaded and executed, then it will resume parsing and continue on. We can see the impact of this by using a simple example with a file that we're going to attach, a JavaScript file with a 2.5 second delay. Now for this, I'm using Slow Files, which is a very straightforward service built by Ryan Townsend and Harry Roberts. I use it a lot though. It lets you pull in a JavaScript or CSS request with a delay attached, and it's really helpful for things like this. Like, I want to visualize what is the impact from a performance perspective of loading a file in a particular way. So I can add that delay, I can see that exaggerated impact and see exactly what's going on. So inside of Chrome DevTools itself, we've got this performance panel. And what we're seeing here is we've got the network activity, and underneath that we've got all this main thread activity. That's those little slivers down at the bottom. So what we're going to do is we're going to zoom in here on the Slow Files request. This is our JavaScript request that I talked about, that 2.5 second threshold, delay. You can see it takes 2.67 seconds or so to arrive in this case. So let's go ahead and zoom in on the actual main thread activity now. And we're going to move all the way over to when we first find that file to see what the browser's doing. So here we have the request has been initialized. We look down on the main thread to see what's going on. We see the request being sent. And right here we see the HTML being parsed. So at this point we see that what happened was the browser parsed the first 6 lines of our HTML. Then it found this blocking script element, and it went ahead and made the request for that script element. Now notice what happens to the main thread as we start to move back to the end of this file request arriving from the network. So again, we've got our HTML. We're going to zoom over here, and try to get to the end. Notice how there's almost nothing happen on the main thread at all until finally that file arrives here. Now, if we go down at the end, we can see the response received, and we see the browser starts resuming the parsing of HTML finally on line 7, a full 2.8 seconds later. That's what JavaScript does out of the box. It is parser blocking, and that, as a result, it blocks display of the page, and it blocks the HTML parser from doing any additional work. Now, this was an issue that, outside of those blocking script elements, sometimes it can be a little difficult to track down. Thankfully, we've seen some improvement there from a tooling perspective. The Chrome DevTools protocol now ships a flag in the trace events to indicate whether a resource is render blocking or not. At web page test, we've started taking that render blocking flag, and if we see it, we put a render blocking icon next to it to signify that this is a problematic request. So in this case, requests 4 and 5, you can see we've got a blocking JavaScript file and a blocking CSS file. So how do we fix this? Well, the first thing we could look at is adding the async attribute. So here's our same script, but we're going to use async instead. Now this changes that loading behavior in the browser. Now, when the browser finds the script element, it will download the script element in the background while it continues to parse the HTML. Now, as soon as the script arrives, it's still going to stop everything at that point to execute the script. Async means that the downloading is done in the background, but the execution still could potentially be blocking. And once that execution is completed, then we finish up whatever parsing work we have left. So this means that async blocks the parser when the script arrives, which means it's a potentially blocking resource. If that script arrives before we get something out on the screen, it blocks display of the screen. If that script arrives after we get that initial paint, well, then it was non-blocking in that situation. So that Chrome DevTools flag that we mentioned, they're giving that render blocking status of potentially blocking for these sorts of resources. So again, in web page test, if I click on a request, I can see that surfaced right now, marked as potentially blocking, meaning if it arrives before start render, it was blocking, otherwise not. Going the next level, taking this even further, we can use the defer attribute. So when a browser comes across a script with a defer attribute, what it will do is it will request the script, download it in the background, and then it will continue all of its work. It will parse the rest of the HTML. It doesn't execute that script until all the HTML has been parsed. It defers the execution until the very end. From a performance perspective, this is our best approach. Unfortunately, when I was digging into this data for the Web Almanac, that 2020 version, we only found the async attribute present on 12% of the scripts, and defer was present on 6% of the scripts. Considering the massive performance improvements we can get by using these two attributes, those results are a little bit discouraging. Now, it's possible we have some visibility issues here. As I said, it can be tricky sometimes to tell if it's blocking or not, particularly if you don't spend all day looking at those kinds of things. So I'm hopeful that by having that flag and having those indicators surfaced in web page test, eventually surfaced in Chrome DevTools, almost certainly surfaced in other tools that might be consuming that same data. I'm hoping that visibility leads to broader adoption of these two attributes, because there's a lot of low-hanging performance improvements we can get from using them. Now, the other angle of looking at this 427 kilobytes of median JavaScript bytes that we send down, the thing that jumps out to me is when we dug into this, we found out that 35% of that is unused. So in other words, we're shipping 427 kilobytes of JavaScript, but during that initial page load process, we're only using about 2/3 of that. The rest of it, maybe we need later, maybe we need for, when a user takes a specific user interaction or routes to another page, but we don't need it right away. Identifying this unused code is getting easier. You have tools that you can use in your build process, like Webpack Bundle Analyzer, that lets you kind of see the breakdown. To get that coverage, we have things like Lighthouse now shipping with the tree map plugin. But the one that I've been using for a very long time is a very long time, at least feels like a long time. In real world years, it's probably not that long. This is kind of like dog years versus people years. But Bundle Wizard. Bundle Wizard is a great utility. You can run it from your command line, pass it to a site's URL. And what it's going to do is it's going to go out and find all the JavaScript, figure out how much of that, loading it up, like I believe in the background on Puppeteer, watch how much of that is actually used. Then it's going to give you a report that shows you both where the file size breakdown is coming from, as well as how much of each of those different bundles and files are actually being used during that initial load process. So in this report, this is a Reddit report. You can see the resource maps for a few files, which is why we have those detailed blocks telling us all the individual pieces in the JavaScript file. In the case here, what I've highlighted is this HTML5 stream player /index.jsx, which is part of the legacy comments page bundle. And it's red because there's not very much of that code that's actually used. In fact, it's saying about 4%. Which is almost certainly just a simple little installation thing, right? It's not actually doing any work right now, probably because my guess is, A, it's legacy, so maybe it's not used at all on this particular page, or it's just one of those things that's not going to execute until the user takes some interaction. So when we see something like that, when we see these orange and red blocks, these low coverage things, those are indications that, hey, maybe we can take a different approach to bundling to try and push those off to a different bundle. Maybe we can lazy load that bit of code, something like that to break it out and get it out of that initial path. Another one of my favorite tools when I'm looking at things like this is Bundlephobia. Bundlephobia is a great site. There's actually some great tools built on top of this as well. But what it lets you do is look up any particular package or bundle. So in this case, Moment, the popular date manipulation module, and you can see the bundle size for minified plus gzip, an approximate download time, a bunch of other information. The thing that really I like about these is that it shows you similar packages. So, it says, hey, we've got Moment, you're looking at it, but there's also these other date manipulation libraries that may be able to help you. Day.js is only 2 kilobytes. Date.fns is 16 kilobytes. We can see that they're significantly smaller. We also have this little leaf icon that indicates that it's tree shakeable, meaning that our build tools, when configured properly, may be actually able to weed out some of that excess weight. Along that lines, it does depend on how we're importing those modules into our actual projects. I had one client that I worked with when I was still doing consulting full-time, where they were using the AWS SDK. And this was how they were importing it. They were really only using the Cognito identity service provider from the SDK, but by importing it in this way, the entire SDK got pulled into their bundle. When we switched that line to this, which was we just required directly the full path to that individual provider, we ended up reducing their parsed bundle size by 1.65 megabytes. So now disclaimer, usually you're not going to get that massive an improvement from 1 or 2 line change like this, but it does make a good story to tell. Now, most of the time you're going to be chipping away at that iceberg a little bit, but this is the making sure that you're paying attention to how you're importing those modules and components is important. The other thing that I think can help us here in terms of size is just having better defaults. I worry a little bit that right now our default posture is to err on the side of popularity or dev convenience rather than what actually may be the right technical solution for us. One of my favorite examples here is Preact versus React. I am a huge fan of Preact. If you're not familiar, Preact is a fast 3K alternative to React with the same basic React modern API, which means that if you're comfortable writing React, writing in Preact is a seamless transition. In fact, it works out of the box with a lot of the React ecosystem. That lightweightness obviously helps quite a bit from the bundle size perspective. I did a workshop one time where we did a half-day hackathon, and in those 4 hours or so of the hackathon, one of the teams actually went and rechanged their entire, swapped out React for Preact. And they had time to spare because I think the last hour or so was just us sharing findings from each individual team. So sometimes that migration is very, very quick and painless. Not enough companies do this. I feel like we all kind of reach for React way too often. What I'd love to see that default posture is if you're going to or considering a React-based application, start with Preact and use it until you can't. Then pull in React. I joked the other day that I think some of this could be positioning. Preact calls themselves a fast alternative to React. I feel like maybe React should change their tagline to be a slow, heavy alternative to Preact. And we see what the branding and the positioning does there in terms of adoption. We have seen some information of this, like some companies talk about this, most recently Etsy. Etsy, they posted on Twitter, one of the developers there, that they switched officially now to Preact. They gave a lot of information around like why they made that decision, why they made the switch. Of course, what jumps out from our perspective of our conversation here is that Preact bundle was about 6K gzipped versus 38.5K gzipped for React. It's not just about the bundle though. Again, going back to Jeremy Wagner, who we mentioned earlier, he wrote a great article on CSS tricks where he took an example. He built a mobile navigation and he had it triggerable in 3 different ways. You could, one version was triggered by a React component, one by a Preact component, and one by vanilla JavaScript, just add event listener. And what you see here is the time that it took for that navigation to open as measured inside of Chrome DevTools. So Preact is across the board here is 3 to 4 times faster. The code that it took to execute to open the navigation. And vanilla JavaScript's even faster than that. Half the cost of Preact, sometimes even lower. So it's not just about the bundle size, but about that execution size. And this is an important piece. I think we talk a lot from the performance perspective right now around how do we reduce our bundles? How do we get our JavaScript size down? And that's all great stuff. That's important. But it's not just about the size. It's about the execution as well. How much time are we spending on that main thread? Going back to Jeremy's chart from earlier, doing processing, doing code execution, because that stuff blocks the user from doing things they want to do. I did some research into this a little while back where I looked at a bunch of URLs on HP Archive to try and see, what's the processing breakdown based on the things that we use. And so what you see here is a graph that shows a breakdown of the mobile processing time on the main thread related to JavaScript for all sites, just sort of as a comparison point. And then for sites with jQuery detected and Vue detected in Angular and React. So the line all the way to the left signifies the P10, the 10th percentile. To me, this is like pretty much the best case scenario. The overall median is about 356 milliseconds. And you can see that with each framework that we're using, it's getting a little bit slower and slower. With React, that 10th percentile, that best case scenario is 2.7 seconds. The 90th percentile is what's really concerning to me. That's where we see, the overall is around 10.4, 10.5 seconds. But then you jump up into something like React again, and we're seeing about 20.8 milliseconds, 20.8 seconds for actual processing time on the main thread on a React-driven site. Now, to be fair, this chart is looking for, does this framework exist? When I was showing this data to someone, they pointed out, well, what if they're in the middle of a migration? What if there's multiple frameworks? So I decided to look at the processing time when only one framework was detected. The interesting bit about this is React gets worse at the 90th percentile when it doesn't have jQuery next to it. It turns out React and jQuery are paired a lot. A lot of people are making that migration. The 10th percentile gets a little faster, about 300 milliseconds faster. The 90th percentile gets a good 4 to 5 seconds slower. So it's actually worse when it's on its own. So we spend a lot of time with these sites, with these sort of modern SPA, virtual DOM-driven frameworks, a lot of time processing and executing that code on the main thread. And so as a result, when I'm analyzing sites, I see a lot of this. This is, again, Chrome DevTools. All that yellow is script execution, script-related work. And the ones that are flagged here with the little red triangle, the little red warnings, those are long-running tasks. Those are tasks that take 50 milliseconds or more. This is a React-driven site. I have about a 4x CPU throttle off my MacBook Pro, so still a pretty powerful thing. But you can see there's multiple long tasks all over the place. And this is a fairly common pattern that I see with single-page applications in particular, where up front we have a really massive task as you evaluate your primary bundles, in this case that 2.5-second task. That's React getting things set up, hydrating the DOM in this situation. I know there's work being done around progressive hydration in React, so we can break this up and only hydrate parts of the DOM. But sometimes I feel like, we're inventing problems to fix them, kind of a thing. But certainly one of the first things you should be tracking on any JavaScript-driven site is this long task behavior. So you can do that using a performance observer. Here we can set it up to watch for long tasks and then beacon them off to analytics. The primary way of looking at long task data right now is to look at total blocking time. So total blocking time looks at all of the tasks on the main thread, specifically those long tasks, those things over 50 milliseconds or so. And it only gives you the total of the chunk over that 50 millisecond threshold. So for example, instead of looking at this 200 millisecond task as 200 milliseconds, it reports it as 150 milliseconds. The 150 millisecond task becomes 100. And so on. And anything under that 50 millisecond threshold is ignored. So in this case, we have 550 milliseconds on this example for the main thread for total blocking time. Now, one of the things that you'll see if you start digging around the web, our total blocking times are pretty slow. We don't do a great job with this metric. Unfortunately, this metric is primarily used in a synthetic setting. In the real user data, what we're using, what Core Web Vitals, the initiative from Google, what they've incentivized is the first input delay metric. And I think that's a step back from total blocking time. To be fair, I did not anticipate that when it first came out. I don't think that anybody did. But I do think now, in retrospect, having seen this metric out for a bit, it's actually a step back in terms of accuracy, in terms of impacting how things are impacting the actual user. So if you look at the bottom here, first input delay is measuring between the point where that browser receives the first user input and when the browser is free to start responding to that user input. The key there is start responding to the user input. We'll come back to that in just a second. If you look at Crux data, Google's Chrome user experience data right now, 99.9% of desktop URLs get a good first input delay score. 88.7% of mobile pages get a good first input delay score. Those numbers look great. In fact, compared to largest contentful paint and cumulative layout shift, the other Core Web Vitals, we are acing the FID comp thing. We are doing great at this particular metric. Unfortunately, FID's a bit of a fibber. Here's an example of a keyboard interaction from another post on web.dev. You can see here what we've got is we've got a long-running task. That's the purple. And you can see where the user presses a key for this key down delay. Let's focus on that, the keyboard interaction up front here. They press the key. Now there's a key down event that fires. That key down delay is that short little sliver there between when they press the key during that one task that was running to when the browser is able to start handling it. But notice that you have these key down handlers and key press handlers that fire as well as part of that event. None of that is captured right now by first input delay. So we have the actual duration of the event is substantially longer than the actual delay that we're measuring. To put this in a real example, this is from an application that my wife was using one night. And she was like, this is really slow. And so I'm a nerd. So of course I fired up the performance panel. This is a click event. It takes 1.1 minutes. That's right, 1.1 minutes on a MacBook Air, so not a underpowered machine. The first input delay came in around 30 milliseconds or so. This whole 1.1 million, as far as this metric was concerned, or 1.1 million, felt like 1.1 million. This 1.1 minutes, as far as the metrics were concerned, just didn't show up. So there's been work inside the performance working group, and Chrome's been involved in this, to come up with a better way. Instead of looking at this delay, look at that entire duration. This is called the event timing API. The idea being here is if we could look at when the event is first triggered or requested to when that event actually completes, we get a much better picture of what actually happened and how much that actually slowed the experience down from a user perspective. So if we switch to event timing API from first input delay, we go from about 30 milliseconds to about 66,000 milliseconds for this particular interaction. I cannot wait until we get event timing API rolled out there, and I assume at some point I would highly anticipate it's going to replace first input delay as a web vital. When we get that, it's going to be a much more accurate view of how our sites perform in the field. And generally speaking, it's a trend, right? Better metrics equal better understanding. Anytime we get some better level of tooling, some better level of metrics, we give a richer understanding of what's actually happening, and at least the new optimizations and new insights. One of the areas that I think is on the cusp of benefiting from these improved metrics and tooling, and that I think is going to be really important in a little bit, is memory. We don't talk about this as much when it comes to a performance perspective, mostly because the tooling around memory from a front-end perspective is not that great. It's not super robust. It's pretty new. And we don't have a lot of metrics around this. There is one that I'm pretty excited about, shipped in Chrome 89 if your site meets certain security requirements. It's called the Measure User Agent Specific Memory API. And what this does is it's going to report memory use that is related to JavaScript and related to DOM elements for your site. So you can have this running, and whenever you get the results back, you can beacon those back. And this way you can actually start to get real user data about memory usage of your site and how much memory are you consuming. Now, the security contexts are a little bit difficult. There's a few hurdles you have to run through. So right now it's tough to get good run data at scale, but synthetic, we can fake it. So what I did is I took the top 10,000 URLs and I fired them up in web page test. I used a custom metric or a custom web page test metric to return the memory breakdown so I could see how many bytes of memory each page was using. And I passed a couple Chrome flags to turn off the security features that blocked this API from running if they're not present. So this lets me get this metric for all of the top 10,000 URLs. And the data came back and it was a little scary. I don't know what I was expecting to see, but it was certainly more usage than I would have anticipated or guessed. It turns out that somewhere around that P25, that 25th percentile, we're using about 4.8 megabytes of memory on both desktop and mobile. By the time we get into that 75th percentile, we're at nearly 20 megabytes. At the 95th percentile, firmly in that long tail, now we're getting close to that 40 megabyte range. These are big numbers, but they can start to give us some sort of a gauge, some sort of a benchmark to look at. And that was the goal of this. It's not necessarily like we're missing some pieces here. We don't know at what point does this impact user experience or anything like that. We need RUM data for that. But at least based on this, we can extrapolate like, all right, what's good look like? So if we do the same sort of approach that the Core Web Vitals took, we put that 25th percentile as good, that 75th percentile or so as needs improvement. Then we figure out like anything under 4.8 megabytes is good. Anything between 4.8 and 19.4 needs improvement. Anything above that is in that poor category. Now, the other thing with memory usage to keep in mind is that this is a measurement of initial page load. This is what the page is using in memory when it's first loaded. Where memory gets more interesting and the pieces that are going to be harder for us to sort of put a benchmark around are interactions, because once you start interacting with the page, that's where we start to see memory leaks and that memory data spiking and the memory usage spiking. Unfortunately, I ran a bunch of different, maybe a dozen different tests where I was looking at some of the URLs that I had already captured. And it turns out that basically if you have a site with any of these SPA architectures, roll a dice, land on one, and you're probably going to find a memory leak. They were all over the place. So here's the Vogue homepage, right? So this is a React application. There's a lot of lazy loading happening here. Loading in images, loading in different stories and different components as it's going up and down this page here. When I tested the Vogue page, the home page, the initial load, it was about 36.6 megabytes of memory usage. After scrolling to the bottom, we were using about 84 megs. Chrome has a memory tool visualization inside that performance panel that lets you see heap size. Keep in mind the reporting is going to be a little different. Each page is going to be different, so the numbers aren't going to be perfectly aligned here. But this is what I saw over the Vogue scroll, right? You can see that JavaScript heap, that's our blue line, and the number of listeners here, it's our yellow line, are going dramatically, especially the listeners, going dramatically up and to the right, which is not what we want. Like, that's great for stocks and things like that, I guess, but not what we want to see when we talk about memory usage. Another example, Lego. Lego is, again, a React-driven site. And for this one, again, I saw a significant memory increase as I went from, moved around in the SPA, from the home page to a search to a product page. For this, you can also look at that Chrome actual memory panel has the ability to grab a heap snapshot. And so if we take a heap snapshot of before and then after we've navigated through those pages, we can compare the two and see what's going on. So before, you can see in this case, it was about 21 megabytes roughly-ish, and about 1 to 2 megabytes higher by the time we'd gotten to that next navigation. The biggest increases here were memory related to code and strings and JavaScript arrays. Looking into each of those heap snapshots, we get a detailed breakdown here of what exactly is comprising that heap snapshot. In this case, I've got it in a comparison mode so I can see the difference between the second snapshot and the first. And I've got it ordered by size delta. So again, array and string related memory usage jumps right to the top. Another really good starting point for you with these heap snapshots, just to see like typical low-hanging memory leak stuff, is to check for detached elements. So if I search for detached in here, now I'm seeing like these are all detached elements. These are DOM nodes that were removed from the page. They're not present in the document object model anymore, but JavaScript still references them. So the browser's garbage collector can't remove them. And so they stay in memory. So for each of these, I could dig in and, figure out, okay, why do we have so many different elements and attributes that are lurking about still? There's something happening in the code here that's not freeing those things up. So this is another, between the analytics tool, the analytics itself, the web page test analysis, the memory panel and performance inside the dev tools and the heap snapshots, there's a few different visualizations we can start to use to try and dig in. None of this should be surprising though, right? Like I haven't told you anything super exciting. More processing time, more memory usage. If you've got more JavaScript, it means more work. That complexity, though, is I think what's at the heart of so many of these issues from a performance perspective, as well as the accessibility side of things. Again, remember, WebAIM found more issues every time a framework or library was detected than without. The web platform itself does a ton under the hood. Jen Simmons, in an episode of Shop Talk Show with Chris Coyer and Dave Rupert, was talking about building for standards and building for the actual specification and browser side of things, not the front end engineering that you and I do. And she talked about how there was a couple key differences. Like with me building for a site, I can always delete my code later. You can always say, oh, this thing I shipped quickly for my project was a bad idea, get rid of it. But with the web, there's two things that are different. First, once they ship it, they don't get to change it and ship it again. Like that never happens. If something is crappy at the beginning, they're stuck with it. So they have to make sure it's right. The other thing is they're not solving for one individual website. It's solving for Facebook or YouTube or CodePen. You're solving for the entire web and every use case at all the same time. In other words, there is a ton of thought and planning that goes into everything that makes itself into the web platform. When we start to throw things and try to overrule that or bypass it with JavaScript or custom work like that, we start to lose a lot of those ingrained benefits. One of the things I see a lot in sites, and I know it comes up fairly often, is divs or spans instead of actual buttons. I've seen these inside of forms where there's no submit button. It's actually a div or a span that kicks it, and JavaScript is taking over the entire thing. There is a dramatic difference between how the browser treats these two elements natively. If we look at the Chrome Accessibility Inspector for the div, and under these computed properties, there's nothing here. This is a generic role with some static text. There's nothing about it at all that indicates to any accessible tech what the heck this thing is supposed to do. The button, on the other hand, even without any labels, even without other markup to go around with it, we know that it's a button. We have a tab. It's focusable. We can put our focus on it. We have the contents related to it. There's a lot more information right away. There's also some built-in functionality. We have the ability to do things like tab onto it and press space as an alternative way of interacting with the button. If we're going to do that with our div, we have to hook up a whole bunch of JavaScript. I mean, even just to get it to start to do some of the things that the button does requires that we manually go in and tell it it's focusable with tab index. And we can use an ARIA role to tell it it's a button. In fact, that is often the fallback here, is we use something like ARIA attributes and things like that to try and indicate when we're doing these custom elements, like this is what it actually is from a browser perspective. But interestingly, AIM also found that ARIA correlated to higher detectable errors. With the more ARIA attributes that were present, the more accessibility errors there were. When we try to take over what the platform is providing us and do our own customization on top of that, we often fall short because that's not the way we operate. We don't have the time, or we don't have the experience or the different perspectives to be able to consider every possible use case. So we're going to miss things. It's not surprising when things fall between the cracks. Now, how do we improve this? Well, the first thing is, don't just look at Lighthouse. When I did the JavaScript research, there was a really, really low correlation between JavaScript usage and Lighthouse accessibility. Now, this is in sharp contrast to the WebAIM results, right? Like WebAIM showed a very common connection, very clear picture there. Lighthouse, not so much. And the reason is that the Lighthouse audit is great. It's a good low-hanging fruit starting place. It is not super robust. It is nowhere near as polished as the performance side of things, for example. So step one, I think, is the tools. I am a huge fan of Wave, the web accessibility evaluation tool. You pass it an address, and it's going to give you detailed information about the errors and alerts. It checks a ton of different things. And, it's nice. It's also kind of fun as you're cleaning it up to keep hitting refresh and watch those things go away. But this is a much more robust way of testing accessibility. Even better, bring some of that stuff into your editor. If you're using something like React or Vue or anything with JSX, pull in these ESLint plugins that actually will check for specific accessibility issues while you're writing the code, hopefully stopping you from putting those inaccessible experiences out to begin with. It's all about introducing that healthy friction. That's, making some pause when we're writing our code, when we're rolling out a new framework that makes us consider what the potential impact or consequences are of those things. Because again, everything has a cost. Nothing is free, and that's especially true of JavaScript. I think one of the things that has had a profound impact on my career was a talk from 2008 by Nate Keckley, who was at Yahoo, I believe, at the time. And it was all about front-end engineering and what are our roles and what are our responsibilities. And one of my favorite lines from that is he talks about how we want to have stubborn empathy for our users, for what they need, for what they want, and for what they're going through. And we have to be constantly focusing on what can we do to make all of that better. So I think if there's one thing that kind of, one guideline here for all of this, it's be stubborn. Be stubborn on behalf of the users. Constantly seek ways that we can make their experience better and fight hard for them. And anything that we're going to add has to go through that sort of gauntlet, right? Like we want the friction. We want to have better defaults. We want to be carefully considering what we add to our page to make sure that it's providing the experience that they want from a rich and immersive perspective, but at the same time that we're not giving up on those core pillars of the web, that we make sure it's performant and it's secure and it's accessible. Thank you.